I don't know, this is what he said.
Hi, guys. So let's see. Maybe some of you saw I released the midterm scores. Yeah. Ooh, that was a low average. Man, I did not think it was going to be that low. Any questions on that before we get to the math? All right. Let me remind you of what we were doing last time, which is we were starting on 8.1. Green's theorem, the first of our higher dimensional fundamental theorem of calculus theorems. So it's kind of like you got to do a lot of setting up, and then once you set up the meaning of all the notation, the theorems are actually pretty simple. But this is some of the setup, which is, for one, the orientation of a planar region. I already gave you a lemma 1. What was lemma 1? It said, if D in R2 is a y-simple region, and we have a C1 function on it, say P from D to R is continuously differentiable. Then we had that if you integrate dp dy over the region D, that's the same as integrating it around the boundary, integrating p dx around the boundary. And just to remind you, because we're going to be using it, what that differential form notation means, the dx's. That's when if you have a path integral, some vector field, line integral, some vector field over a path, you may also write that as f1 dx plus f2 dy plus f3 dz. Where f is f1 I hat plus f2 j hat plus f3 k hat. f1, f2, f3 are the components of vector field f. Cool, okay. So today is going to be a bit theory heavy, I think. I'm going to do some proofs. And so I think I'm going to prove lemma 1 for you. I did an example of it last time, but I didn't prove it yet. So I'll prove it for you now. And like I was telling you, the proof basically just comes down to the fundamental theorem of calculus. OK, so here is my attempt to prove that. First, let's draw a y-simple region, say, in the xy plane. It goes from x equals a to x equals b. And then it has some function on top and some function on the bottom. So maybe on the bottom, that's where y is phi1 of x. And then on the top, that's where y is phi2 of x. Then a path surrounding that region would go in the counterclockwise direction. So let me name each of the sides. How about the bottom is C1, the right is C2, the top is C3, and the left is C4. Those are the 4 pieces of the path that surrounds region D, where This is D. So the path that surrounds the region is made up of 4 pieces. Let's just look at, say, one of them. How about C1 of T is the bottom piece? Is one possible parameterization of it might be T phi1 of T for A less than T less than B. Okay. If I integrate dp, dy, dA, let's write that as an iterated integral. That's, how about if I integrate first with respect to y and then with respect to x? And what can I do right now? I can cancel out the 2 derivatives. I'm integrating a y derivative, but I'm integrating it with respect to y. So this is exactly where the fundamental theorem comes in, that this is a to b of p of x phi 2 of x minus p of x phi 1 of x. Okay, so that was the most important step. I told you all these proofs, it's just fundamental theorem and bookkeeping. Well, the rest of the proof is just bookkeeping. So let's see what some of those path integrals look like. How about the integral on C1, the bottom path, this part? So on C1, if I integrate p dx, let's see. Using the parameterization that I wrote right up here, you know what? I can just use x instead of t. We really don't need this independent parameter t. So writing it with x instead of t, this is just, let's see, x goes from A to B. P evaluated on the path is p of x phi 1 of x. We're integrating dx. So if you don't understand why that's the case, you should convince yourself of this. Similarly, how about if I integrate along the top path, C3? So integral of p dx on C3 is, it's basically for the same reason, or for a very similar reason, we're going to get the integral from A to B of p of x. Now it's phi 2 of x, except, oh, I didn't account for the orientation. Instead of moving left to right, we're moving from right to left. Or in other words, like from B to A. Or I can just put a minus sign in front, which is what I'll do. Okay. So let's put this all together. Oh, what about the 2 sides? So on C2, what's the change in x along C2? 0. It doesn't, yeah, x is constantly equal to b. So there is no, dx is 0 on that portion of the path. Similarly, on C4, x is a constant, so dx is 0. So putting this all together, the integral of p dx over this entire path c plus, which is the integral over c1 of p dx plus the integral over c2 of p dx plus the integral over c3 of p dx plus the integral over c4 of p dx, that's how piecewise paths work, is, okay, so the first two of the terms are 0. Right, this one's 0, this one is 0, and the first and third we just computed to be integral a to b p of x phi1 of x minus p of x phi2 of x, which is this what I want it to be? Oh, yeah. So compare this and this. They only differ by a minus sign. Thus, I get that this is equal to the negative of d. Cool. Any questions? So lemma 2 is similar, kind of like analogous, but with y in place of x. The only difference with lemma 2 is the orientation. So lemma 2 is as follows. If D in R2 is an x-simple region, and we have some function q from D to R is C1, then the double integral of, now it's dq dx, is equal to the line integral of q dy The only sort of meaningful difference between this lemma and the previous lemma, does anyone see what's different between the two lemmas? There's no minus sign in this one. Yeah, what? Anyone know where the minus sign went? It has to do with orientation. It had to do with the fact that in a y-simple region, as you move along the top, you're actually moving right to left. But in an x-simple region, when you're on the right, you move up, and when you're on the left, you move down. So it just has to do with the relative orientation of x and y. Any questions? Okay, well, Green's theorem is just the combination of these two lemmas. I'm just going to put these two lemmas into one formula, and that's the whole of Green's theorem. So combining lemma 1 and lemma 2, we have that if D in R2 is a simple region, and we have two functions, let's say P and Q are both C1 functions on D, then the double integral of, okay, dq dx minus dp dy is equal to the line integral p dx plus q dy. And there's your Green's theorem. And like I said, the proof is just you're writing lemma 1 and lemma 2 in the same formula. So notice the region that Green's theorem applies to. I said simple regions, so they had to be both x simple and y simple. Fortunately, we can now generalize it to a much broader class of regions. And I'm telling you that we can generalize that theorem to any region that's a union of simple regions. Let's say finite union. Actually, the most general region that Green's theorem would be applicable to is a non-trivial question, but beyond the scope of this class. So for now, for us, suffice to just say, if you can break it into a few smaller pieces that are each simple regions. Let me show you a picture of what I'm talking about. So suppose, how about we have an annulus? Let's say that region D is this annulus right there. Is it an X simple region? How about, what do you guys in the back say? Is that X simple? Well, can I draw a horizontal line through it that passes through the boundary in more than two places? Yeah, so it's not X simple. Similarly, it's not Y simple. It's certainly not simple, but I can chop it up into simple pieces. Like how about if I cut it into 4 pieces? Imagine just getting out a scissors and slicing it up. So let's say if I look at the piece in the top right, okay? That's this piece. Let me call it, how about D1 is up here. Okay, is D1 a simple region? D1 is simple, indeed. So Green's theorem applies to D1, where this is the clockwise, oops, sorry, that's wrong direction. Where this is the clockwise orientation of the boundary. Okay, now let's look at the piece below it. How about this one right here? I'll call this one D2. D2 is also simple, and the clockwise orientation on the boundary will look like this. Okay, now here's kind of the cool part. Let's say I integrate over the union of D1 and D2. They have a line in common. They share a boundary line right there. If I integrated over their if I tried to apply Green's theorem to their union, what would happen when I do the line integral in Green's theorem, and one of the line integrals is going left, the other one, it's of the same thing but in the opposite direction. they're just going to cancel each other out. Yeah, so you'll get plus and minus the same thing. It'll be as if, are you watching? This boundary never existed. This is supposed to be a dramatic part of the lecture right there. Yeah, it just like disappears because the two line integrals cancel each other out. Similarly, of course, we could do the same with the left piece, right? And once again, we'll get some cancellation where they share a boundary. And then, just to make the picture complete, we could do it on the upper left piece. And once again, we'll get cancellation of where it shares a boundary with its adjacent region. Well, what's left is this disk where the outside goes counterclockwise. The inside actually goes clockwise. And all the other line integrals canceled each other out. Okay, so that's how it works. That's how you can break down a more complicated region. If you can slice it up into smaller, simple regions, all the adjacent boundaries will cancel each other out. And here's the rule for the orientation of the boundary. I mentioned it before, but it's like if you're walking along the boundary, just make sure that the region is always to your left. Like I said, nothing special about to the left. It's just they had to choose one, so it's to the left. That's the rule. If you walk around the boundary, the region should be to your left. And that's how you know how to orient your boundaries. Okay, so the book has a nice picture of like a golfer walking around the hole, and as he's walking around, he's always like pointing his golf club, at the hole with his left hand. Any questions? So occasionally we're going to talk about regions to which Green's theorem applies. So this is what we're talking about when we say regions to which Green's theorem applies. Cool, okay. Now, I would show you an example of applying Green's theorem, although in general, the examples are kind of a pain in the butt, right? Like, you got to do like multiple line integrals. It's of a vector function and a 2D integral. So I don't really want to do one because I already did one basically. Well, I kind of did half of an example. So I'm going to let you work out some examples of demonstrating Green's theorem in the homework. I'm going to move on to an application of Green's theorem, which is to find the area of a region. So we've already seen formulas for the area of a region. Here's one you've never seen before, though. This one's new. And it actually allows you to compute some things that were formerly difficult. So the new area formula is as follows. If D in R2 is a region that Green's theorem applies to, then the area of the region is the integral of, it's 1/2 the integral of x dy minus y dx over the boundary of the region. And here's a little proof of that. Any guess how we prove that? Well, look at Green's theorem. What if this integrand was 1? Then we would just, what's the integral of 1 over a region? The area. If you integrate the function 1 over a region, you just get the area of the region. So I'm just going to ensure that that integrand is 1, which I can do in multiple ways, but the most symmetric way is if, how about if, which function was it? If Q is, if Q of x and y is x over 2, and P of x and y is negative y over 2, then what's dq dx minus dp dy is equal to 1. Right? It's a half plus a half, which is 1. So we get that the area of the region, which is the integral of the function 1 over the region, is, by Green's theorem, the integral over the boundary of the region of, let's see, q dx. Yeah, so x over 2 dx. No, wait, which one was it? It was q dy, sorry. Q dy. Let me look at this one. Yeah, q dy and p dx. So q dy is x over 2 dy plus negative y over 2 dx, or I could just write that as 1/2 x dy minus y dx. Any questions? How about, so what was your name with the bleach chair? Nick, yeah, Nick. What's the little box mean? This one. Why am I writing all these little boxes? Well, I've written 2 of them so far. Why do mathematicians write boxes at the end of proofs? To let you know that it's the end of the proof. Yeah. Mm-hmm. Cool. Okay, so here's an example. Let's do the hypocycloid. Yeah, this is kind of a cool example, which I could probably spend far too long talking about. When I was teaching in the summer, I took a deep dive into hypocycloids, epitrochoids, hypotrichoids, cycloids. Like, they're neat. They obey pretty cool mathematical properties. You can make them on a spirograph. If kids today probably don't know what a spirograph is. I barely did when I was a kid, but I did see a few of these toys where you could construct these shapes that you get by rolling circles around other circles and tracing out a certain point on the boundary. So in this case, let's look at the function x to the 2/3 plus y to the 2/3 equals 1. The graph of this shape looks like, what it looks like is, do we have any Pittsburgh Steelers fans in the audience? Damn, okay, that's my team. Well, it looks like a shape that's on their logo or their helmet, but there it is right there. So we want to find the area of this region that's bounded by that curve. And if you try to do it using traditional methods, you'd probably get stuck and not know what to do. I wouldn't. You get a really ugly integral. So you can just take my word for that. Or we can try using our new theorem. So here's the answer. Is we parameterize the boundary of D with cos cubed and sine cubed. For t between 0 and 2 pi. So it's easy to verify that cos cubed and sine cubed satisfy the equation of the boundary. Oh, by the way, let me show you a picture of some hypocycloids. So yeah, these are what some of these shapes are. Like, there's a few examples of some different ones, and they can get way cooler. I should dig up some of the problems that I gave my summer session students on this, like, or handouts that I gave on these, because there's so many like cool shapes you can make. You can design your own and come up with all these cool shapes, and they've got all these sort of bizarre properties that are relevant to problems that the Greeks have been wondering about, and equations of motion. Okay, so let's plug in the formula. Formula says that the area of the region is the integral over the boundary of x dy minus y dx. So that's the integral from 0 to 2 pi of cos cubed t dy. Let's see, that's 3 sine squared t times cosine t plus minus, oops. So minus y, which is, what's y? Y is sine cubed t, dx is 3 cos squared t times negative sine t. This is the integral of, okay, what do we get? 3 cos to the 4th t sine squared t plus 3 cos squared t sine to the 4th of t. We can pull out a cos squared sine squared, and we get, oh, I forgot a 1/2. Yes, there's supposed to be 1/2 in front. Thank you. 1/2, 1/2, 1/2. Cool. Okay, so I get a 3/2, 0 to 2 pi. After pulling out cos squared and sine squared, well, I just have cos squared t sine squared t dt. Huh. How the heck do you integrate cos squared sine squared? Who's got an idea how to integrate this one? Yeah? Okay, so that's normally what you would do, except you still have like an even number, because you have an even number of cosines and sines. So that's normally how you would approach like a product of sines and cosines. It doesn't help here because they both have an even power. This is from the like trig substitution you learn in 20B. So you have to use a double angle identity. I'm going to use the following. Use that sine 2x is 2 sine x cos x to get that this whole thing will be equal to 3/2 0 to 2 pi 1/2 sine 2t squared dt. But I still now have to integrate sine squared of 2t. Okay, how do I do that one? Yeah? Sorry? Power reducing formula? Oh, yes, exactly. Yeah, that's exactly right. Cool. Yeah, so I can write that again. So here's another trig identity, which, why am I doing this example? There's a few reasons. One of them is to remind you of these trig identities. Yeah, they're good to know, man. So now let's use the fact that sine squared x is 1 minus cos 2x over 2, and instead of x, it's 2t. So I have 3/8, 0 to 2 pi, 1 minus cos of 4t over 2 dt. The cosine term disappears because it's periodic, and I just get 3/8 times 2 pi times 1/2 is 3 pi over 8. Cool. Okay. Any questions? What else do we have? Okay, so there's a few other ways we can write Green's theorem. As I was telling you, there's like more elegant ways we can write it. So I'm going to show you 2 other ways we can write Green's theorem. One of them is using curl. So if f is equal to some vector field on the plane is p I hat plus q j hat, and d in R2 then you can write Green's theorem using curl. Right? You can write it as del cross f dotted with k hat. And you can write the path integral as f dot ds. So here's a quick little proof of that. What is del cross f? When f just has components p and q? It only has a z hat component. If you work it out, we actually discussed this before last section. It's dq dx minus dp dy times k hat. So when we dot del cross f with k hat, we just get dq dx minus dp dy. Anyone recognize that expression? Who's been paying attention for the past few days? Yeah? It is, yes. I mentioned it, yes, in an earlier context, that's the scalar curl of F, too. So you're both right. But since it's the integrand of Green's theorem, right, so damn it. Why does this do that? When we integrate this curl, we get dq dx minus dp dy. Which by Green's theorem is the same as the line integral of pdx plus qdy. But that's the same thing as the line integral of f, right? Like by definition, by what I was reminding you at the beginning of class about the differential form. That's just exactly f dot ds. I know some of this is just notation. I know, like that's higher mathematics. You could argue all of math is notation. Seriously, depending on how trivial you think the result is. But you know, if there was such a thing as God, he would probably think that all results are trivial, right? The flying spaghetti monster, he believes all results are trivial too. Okay, let's write it another way. Wow, I'm making good progress here. All right. How about if we let D in R2 be a region to which Green's theorem applies? As usual, with positively oriented boundary C plus, and F is P I hat plus Q J hat. It's a vector field. On D. Then, okay, let me write the formula. The integral of del dot f, that's a divergence. Yeah, divergence of f dA is equal to, and I'll have to explain this part, it's equal to f dot n ds. And what the heck is n? I haven't told you yet. n is the outward normal to the curve. Outward unit normal to the curve. i.e., if the boundary is parametrized as x of t, y of t, then n hat, which depends on t, is given by, I'm going to need more room here. Hold on. What is n hat? It is negative, no, it's positive y prime of t, negative x prime of t, over a normalization factor, so x prime of t squared plus y prime of t squared. What the heck is that? So that's like, let's say this is your region D. Okay, so it has a boundary with some with an orientation. And let's say that this right here is a point C of t. Then the tangent to that point is C prime of t. Cool. I don't know if you remember this, how you can get a perpendicular to a vector in the plane. You remember that, like, if you have some vector here where this is A and this is B, so this is like the vector AB, what perpendicular to AB is the vector B negative A, which looks like this one. So this will be at the point B negative A to make a right angle right there. So that's this vector right here is n hat. Like, it sticks out at a 90-degree angle from the normal. Any questions on that setup? I don't think I don't think I'm going to prove Theorem 4 to you. I feel like we've done enough of that. You can look at the proof in the book if you want. But is everyone clear on the statement of Theorem 4? Yes. You have to evaluate it at each point. So I can show you. I'll show you an example of that next time. I'm not going to have time to. Although we can do the area of an ellipse surprisingly fast. I'm not going to do it now, but you will be impressed at how fast we can do the next example. So I'll pick up there next time.